Hi, good afternoon, everyone. I'm Hamda Al Hosseini, a researcher in the UAE REP program. Welcome to the 10th UAE REP webinar, where we discuss cutting edge strategies and applications in the field of rainfall enhancement. Today's session will focus on sustainable water management strategies to complement technologies for water harvesting from non conventional sources. It is an incredibly important topic, especially as we look into innovative solutions for addressing water scarcity challenges. We are honored to have with us today Dr. Chakravarthi Godibati, the Executive Director of the Water Technologies Division at the Renewable and Sustainable Energy Research Center of the TII in Abu Dhabi. With over 18 years of experience in the water industry, he has been instrumental in advancing technologies for desalination, industrial wastewater treatment, and osmotic energy harvesting. He has had R&D roles at global institutions such as GE, Evoqua, and research institutes like A-Star and Nanyang Technological University in Singapore. Dr. Gadibati has earned his PhD in polymer chemistry from Washington University in St. Louis, USA, and has contributed significantly to the development of the functional nanomaterials, anti-fouling coatings, and novel membrane technologies. Before we start with Dr. Gadibati, I would like to remind everyone that you will have the opportunities to ask questions during our Q&A session. Please just type them in the chat box and we'll address them shortly. Over to you now, Dr. Gadibati.
Great. Thank you very much, Hamda. Good afternoon, everyone who has joined. First of all, I'd like to thank NCM, the National Center for Meteorology, and also the United Arab Emirates Rain Enhancement Program. Me the opportunity. As Hamda has kindly introduced, I come from water treatment, desalination, and downstream process technologies development. So what I'm going to talk about today is more about the after effects of the rainwater management or urban planning, for example. And also we'll talk about some new technologies that are picking up pace recently, like atmospheric water harvesting. Story for basically development or ensuring water security for the region. So I'll start off with a brief introduction about our research center, and then touch upon a little bit of the water security challenges and available approaches that can be implemented in water and Sorry for the interruption. Hi, sorry for the interruption. There's been a disruption basically in the internet connection. I'm sorry. So what I was talking about was the UAE water security, current challenges and available solution pathways. Of course, for the freshwater production, reliance on desalination, as well as newer technologies like atmospheric water harvesting and cloud seeding are basically being used intermittently to generate artificial rain. And of course, there are other challenges like water conservation, where there is produced water, which has a lot of water, but it's used. So they can be technology innovations to extract more water from those sources. And available fresh water generated from different sources needs to be stored. And for that purpose, there are aquifers and constructed wet wells. And in terms of smart utilization, for example, something like agriculture and irrigation, there needs to be more technology innovations where right amount water goes to the right place without any wastage or excess discharge. Similarly, these technologies can be combined with digitization to preserve the freshwater that is being produced with such great cost. And of course, wastewater treatment and reuse, that also remains a very important strategy. UAE has wastewater treatment facilities, and most of the treated wastewater is used for irrigation and landscape purposes. And of course, there are other offstream industries like oil and gas, where there is produced water, which has a lot of water, but it's not used. So there can be technology innovations to extract more water from those sources and create a circular economy and reduce the load on fresh sources. In addition, there have to be a clear mindset and planning about how to deal with climate changes, for example, intermittent and unpredictable storms causing floods and inundation. And digitization is going to be a major focus of my presentation in the next few slides. Urban stormwater management and utilization of that stormwater. Then monitoring and management of the water quality for reuse. And what are the ways that these goals can be achieved is something I'll talk about. In our group, our research focus is mainly aligned with all these concepts that I just showed towards a singular goal of making sure there is water security, which is sustainable and future proof. So that's why we work on production technologies, including desalination, and then distribution of the produced water or even wastewater by basically smart technologies, digital technologies, and also planning for distribution network. And then utilization of that produced fresh water, making sure basically there's right amount of water goes to the right place. And just to give you an example, we look at areas like soil enhancement, where there's not much water is needed. Only the right amount is discharged to an irrigation site. So that saves a lot of money, basically. And finally, we also look at treatment of the wastewater from municipal and the industry sectors, and how that treated wastewater can be used for different purposes. And of course, there are specific targets, technical as well as strategic. For example, desalination, as many of you might know, is a very high energy intensive technology. So how can we reduce the energy consumption in that process and also extract more fresh water for less energy? Then basically usage of the recycled water, how can we increase that from the current 60% to more than 90% in the country, and also reduce water leakages in the distribution networks. And basically how do we harvest non-conventional freshwater sources? Of course, rain enhancement program is one thing, but also moisture in the air, how can we harvest that? and use that water for decentralized agriculture landscaping. Of course, in the Middle East, basically the main desalination technologies, and there's about 100 million. Most of it is basically in the Middle East and North Africa region. And these desalination technologies rely mostly on reverse osmosis. Until recently, of course, a few years ago, the dependence was more on thermal commercial challenges. The is slowly moving, actually fastly moving toward reverse osmosis-based desalination. So the thermal desalination is a method where, in a nutshell, you evaporate the water from, let's say, the sea, seawater, and collect the evaporated water as a condensate, which is basically have a very and a lot of footprint. And to make it more sustainable, they use the thermal desalination plants usually have to be co-located with power plants where there is a lot of waste heat. So the energy consumption, it takes about more than 80 kilowatt hour. It can reach up to 100, 110. These are very baseline average numbers. These energy numbers can go up even further depending on other weather conditions and the water conditions. There are high infrastructural costs, and of course the water quality. By heating the water at high temperature, it may not remove all the contaminants like volatile organic compounds, and then you still have to treat them further to get the fresh water out of it. And like I mentioned, there are geographic limitations. These plants need to be near the coastlines because of the emissions, as well as the need for power plants and also the proximity to seawater. As an alternative, reverse osmosis, which is mainly pushing water from the seawater side at a high pressure. I won't go too much into the details of the reverse osmosis principle, but it's also a very technologically mature process. It's been around for more than 50 years now. And what you see here are membrane is into different components, and we call elements, and assembly of 100 and of high energy consumption, mainly because you're pressurizing the seawater feed up to 70 bar or even higher to extract water on the other side of the membrane. And what happens is only 50% of seawater comes out as the fresh water, and the remaining 50% remains as a very high concentrated brine. And the usual practice is the brine is discharged back into the sea, which causes marine environmental problems. And of course, there are high operational expenses because there's a lot of things that needed to be used, keep the membranes clean. And of course, as alternatives, more feasible, intensive processes like rain enhancement program. For example, as many of you might be aware, it practically means basically injecting silver iodide or some salt or even dry ice basically into the cloud at supercooled regions where the flares of the chemicals, especially silver iodide, are shot into the cloud, and the updraft carries them to the supercool region, or these chemicals can be dropped from aircraft, basically leading to excessive precipitation and seeding and resulting hails and rainfall or snow. Of course, there are advantages in the way of increased precision. This to control extreme droughts or unpredictable droughts. And of course, there are benefits for a specific area of interest where there is vegetation or where the vegetation needs to be grown. And depending on the cloud conditions, that area can be basically cloud seeded, and the area of a vegetation or the process can be helped there. Overall, this is a good measure, a nice measure to mitigate water scarcity. Of course, even in India, for example, very recently it was used to control pollution. In New Delhi, it was heavily polluted, and the only way was to basically cloud seed the rainwater, flushes the polluted down from the air. And of course, it comes with several disadvantages. Main ones are the environmental concerns, how this process in a particular region could affect the weather patterns or the cloud patterns in the neighboring region, altering climatic conditions. And of course, the other concerns come from the use of chemicals in the cloud that include the salinity of the water. Of course, I mean, there are debates about how harmful silver iodide is, but there is research going on to determine effects like iodism, for example, that result from silver iodide. And of course, there are other methods that are used which did not depend much on chemicals. So I think one of the previous presentations from TII was from my colleagues at Directed Energy Research Center, who are actually specializing, who are actually working actively on laser-induced cloud seeding. And of course, there are additional challenges that need to be considered. It's not just how to produce that rain from the clouds using the rain enhancement program, but also how do we utilize the achieve that. And more importantly, what about pollutants? Because it's not just the pollutant. What about the pollutants in the groundwater? Right? That has several aspects that basically can help with ensuring water security for just for UAE, for any country that is water scarce. And of course, the factors that need to be considered are the freshwater production, rainwater harvesting. For example, in UAE, there's about 200 millimeters of annual natural rain. And how do we collect all whatever we can from that rain? And how do we store safely, not just for immediate use, but also for long-term storage? Stored water, the collected water, to be used for portable applications. And of course, there is a risk of floods, right, from the stormwater. How do we basically plan for mitigating these flood risks resulting from the storm? And there are several approaches, and this is what I'm going to talk about in the next few slides. And it is very important to consider these because, as many of you remember, the Dubai a few months ago, and contrary to popular belief, they were not caused by cloud seeding. They were natural storms. And of course, there were basically floods and storms in LA region back in February this year, and that was a result of cloud seeding. So in both the scenarios, obviously, there have to be more planning and implementation that can mitigate the impact in the future. And how can we harvest that water, right? And of course, the reuse of that treated water, and more importantly, how can the community, people, the municipalities, residential areas, industries, how can all of them be integrated into this engagement to make them stakeholders, basically to change the mindset about saving water or conserving water, harvesting available water or stormwater. Of course, all these factors like the water supply solutions, stormwater management, responsible water utilization, and the wastewater management security. Of course, UAE has done a lot already to ensure the water security. I mean, of course, I mean, there's always more things to do, right? For example, desalination, like I mentioned, is the main workhorse. There's about 7.6 million cubic meter per day desalination capacity in the country. And there are also dams and the rainwater harvesting projects which are Wadi Albi in Ras Al Khaimah. And there are also aquifers for groundwater storage and Liva for long-term storage of the treated water for emergency purposes. So, having said that, I want to move towards basically the similar water resource management strategy adopted by Singapore. I'm in Singapore for the years and implementing new innovations at every step, right from production all the way up to flood mitigation and storage and usage. So just a brief introduction. 6 million people, 750 square meters. So as you can see, it's a very small country. Very limited freshwater resources, about 2,500 millimeters of rain annually, and the freshwater demand is about 450 million gallons per day. And that will only grow as the population grows and the industrialization grows. And without the lack of natural lakes or aquifers, of course, Singapore had no choice. And the main source of freshwater is from what we call four national parks. The main one is not main one. Basically, they all have different percentages of contribution. So one basically source is the local catchment area where the rainwater, stormwater, like the one shown in this picture. It's called a marina wash, about 280 cubic meters per second capacity. And reservoirs, there are about 17 reservoirs in the country. I'll show a couple of pictures soon. Some part of the water is imported from Malaysia. So this is basically 100% self-reliance for the country. So the plan for Singapore is to eventually move towards complete self-reliance and self-sustenance and depend less on imported water. Where industrial and municipal wastewater is recycled and treated standards for industrial usage or even potable water. So some of the water that we drink from the taps, it actually comes from the cycle streams. And this is a big success story that is celebrated all over and replicated in other parts of the world as well. And of course, there are 5 big desalination plants and with the total capacity of 215 million gallons per day. And of course, all these are, tools for making sure there is enough supply of fresh water. But Singapore has placed a lot of attention towards rainwater harvesting, managing the stormwater and wastewater recycling as well. And towards these initiatives, especially the urban water management strategies, all these were planned and implemented a few years ago. There was a lot of extensive planning of time before the development picked pace. One such example is basically use of almost 2/3 of the land around the island, and there is an extensive drainage system, a drainage network that was built along the walkways, along the side of the road, where the water that is collected from rain basically of course, like I mentioned, there are 17 reservoirs. Again, it also helps with beautification of the city-state. But more importantly, stores there has been a lot of emphasis in new developments to go towards something called green roofing, where the buildings are made of green and this green roof or the eco roof is being implemented in almost all new developments in the real estate sector. So there are many advantages for this. So it not only helps environmentally by lowering the temperature, for example, or improving the air water quality, but it also helps with regulating the runoff flow. Whereas rain, of course, the roof is the first thing that gets hit, and instead of all that water running off at uncontrolled of course, sustain the vegetation and also help regulate the flow of the stormwater that can be further treated and collected in the subsequent steps. And another approach used by Singapore was basically something called ABC Waters Design, and which stands for Active, Beautiful, Clean Waters Design Initiative, that was started back in 2006. And this was mainly to harness the full potential of the water bodies, different like at source of the stormwater or the pathways that take the stormwater or even the receptor platforms. At every stage, they wanted to harness that full potential of the water and by integrating those drains or canals with the surrounding environment. And by integrating those drains or canals with the surrounding environment, I mean, they made sure there is an interface between the public body and basically vegetation, greenery everywhere. And also, more importantly, a very well-connected network for regulating the stormwater the stormwater is generated. And for examples are these detention ponds where the water can basically be held after the rain, or the decentralized detention tanks, or even rain gardens, which are bio retention ponds. So all these areas help regulate the flow, slow down the flow of the runoff from the storm. And that water basically slowly is conveyed through the pathways, for example, into the receptor areas. For example, the centralized desalination tanks for communities or a big area. And then that same connection, that the same pathways can be used to convey the water through the final catchment area, reservoirs, or even discharge into the pulse. This is just a part of it for all the new developments in which all the real estate sector has to follow. So the main target is there are three main strategies approaches. So flood prevention using this ABC advanced modeling studies of the hydrogeology or topography of a site, works necessary retention ponds, all these methods can be implemented. Of course, each of these developments will have to comply with the code of practice defined by this ABC design initiative. But like putting and if necessary, a drainage infrastructure needs to be upgraded. So it can happen before or during or after the development. I mean, there is a risk of floods basically happening, uncontrolled, unpredictable. So what Singapore has done is put in place an extensive emergency response plan, mainly to mitigate that impact. Even if there's a flood, the impact is very minimal because there is infrastructural support already in terms of bridges or retention ponds or even discharge into the pulse. I mean, just to give an example, there was this is an actual picture from last November. So what What are the other key solutions that can be used? Basically, the more slightly more mature recently are something called nature-based solutions. So instead of conventional drainages or conventional retention ponds or detention basins, basically you can use bioswales or biodetention basins, areas where the water basically temporarily stays and then runs off, and these basins remain dry between the storms. And of course, if there is vegetation that is grown into this detention basin, called a biodetention basin. And in addition to that, there is a bioretention basin that is shown in the left bottom image. And a typical design is, looks like this, so where the inflow of the stormwater, basically this land has a lot of densely planted vegetation. So what that vegetation does is, of course, it's a sustain stormwater and also regulate the flow of the stormwater, preventing any flood risk downstream. And also it filters some of these contaminants in the stormwater, like sediments, coarse particles, enhanced by using another layer of bioretention soil, which is finer, and it has the capability to remove even more pollutants from that stormwater. So as you can see, it's reducing the storm flow and also filtering and treating that stormwater, at least to an extent that it can be safely discharged into a catchment or a reservoir or other storage areas. Okay. And again, examples of a detention basin and the retention ponds. Retention are more permanent structures where the water can be held for longer periods of time. Of course, the bioretention ponds is where there are vegetation, and it adds to the beauty of the area as well as serves as a water source. So how are these subs integrated? I'll just give you an example of a development of a pre-development design for, let's say, a park or a building that is based on this ABC waters design. So you have the building on the left with the green roof on top. So what does the green roof do? As mentioned earlier, it it basically cleans it up a little bit, and then lets the water flow through, and that water running off of the green roof basically is collected in these small planter boxes, which are, of course, small enough to store water. So what that does is basically reduces the fall of or the flow of the stormwater. It can either be diverted to a local retention tank where the water stored can be used for non-potable application, or it can be run off or conveyed through a series of vegetation, like bioretention swales or the basins, which are more shallow, or even gravel trench, to ensure that that water is properly pre-treated before it's discharged into the waterway. What that does is basically reduces the need for more costly and heavy treatment methods for the water. Okay. Other key strategies the payments. Clear example of into the nearby drainage or sump. It's collected in the sump, whereas the left side of this image shows a porous asphalt where the and the network and all the way to the catchment. Main differences here, and there are several innovations happening in this area. For example, I mentioned the main advantage of having infiltration trenches. Same concept can be applied to the pavements for what they call permeable concrete pavements. They use porous materials in the asphalt layer, where the water can seep through all the way to the subgrade and all the way into the ground, where it can basically be primarily treated and then discharged into the water bodies for storage and utilization. Within the porous structure, mainly to remove any pollutants or contaminants in the water development. And once implemented, I think it'll be a very important measure because that takes away a lot of need for downstream technologies for removing those contaminants. In fact, people are using porous asphalt. So all these, of course, I mean, can be implemented for existing infrastructure or advanced planning for the infrastructure that is going to be built. And of course, not every solution is applicable in every region, but nevertheless, long-term sustainability of the water security and the stormwater management. And none of these technologies are complete without a digital component in it, because digitization or the use of tools like artificial intelligence or machine learning or Internet of Things can certainly achieve a lot of maturity resilience and sustainability against any future events. All of them digitized and can be smart so that we can understand all the risk events and implement mitigation steps well in advance. The specific examples of how the digitization can help. The Internet of Things, of course, there is a lot of sensors in desalination plants or even distribution networks. So the Internet of Things, I mean, you can have those data analytics tools, and that can give us a big picture and very advanced insights and even prediction of events that will help us with decision making about how a specific network or a specific area that is prone to floods can be managed. Digital twins, a very important tool. A lot of countries and regions are adopting this. Mainly, this means like creating a digital twin of basically, which is a smart approach. This help us with a scenario evaluation, because we have all the necessary information there. The infrastructure, the drain, the network, everything is there. So a lot of simulation can be done to evaluate possible risk scenarios. So what happens if as part of the cloud seeding step in the seeding program in this region, there is some unpredictable or weather pattern or flood in another area. So what are the risk mitigation steps that can be planned in the future, right? Again, AI and autonomous systems, that's a very important thing. Bots, like sensor bots or drones, or even unmanned vehicles are being used, not very extensively yet, but in Singapore, in some areas, to monitor the drainage networks or sewer networks for any kind of contamination. So all these tools can. So I think that concludes the first part, and I hope to have conveyed an important message that it's not just the production or the usage that is important. We also have to understand how we can combine all these tools into this platform called Integrated Water Resource Management to make sure no fresh water is produced easily, cheaply, affordably, and that fresh water is used properly, and the waste is managed properly, and any waste, if it can be recycled, should be recycled properly. So another approach, somewhat similar, distant cousin to cloud seeding, is atmospheric water harvesting. Again, it's technically means extracting water from the moisture in the air. And as you can imagine, it's a renewable water source, and you can harness the water anywhere, literally. Wherever there is moisture, there's relative humidity, of course, and certain temperature can be used. And of course, it's the technology itself is such that you can heavily, for example, dig large in remote locations. and having fresh water pumped to those areas for the irrigation could be cumbersome or even costly, right? So in such areas, using technology farms and the irrigation self-sustaining. Without going into much details, there are different types of the atmospheric water harvesting systems. The most prominent and even commercialized methods are, many of you might be familiar, and others are more passive methods where adsorbent materials that absorb moisture from slabs of. So the active method is the refrigeration based method, and there's another more less refrigeration. Of course, all these technologies processes do require energy to convert that water, basically vapor into the water. And the ideal situation is integrating these technologies, whichever basically matures, integrating those technologies with renewable energy sources so that they do not add any further carbon footprint. So the vapor compression cycle, just a quick run through. It's basically depends on evaporation, compression, and condensation. The moisture air goes in, and it gets cooled within those coils because it loses heat to the cooled refrigerant which is flowing in those coils, and that cooled water is condensed and collected as fresh water. Whereas a refrigerant basically is recirculated after evaporation, compressed, and then condensed. Condensation of the refrigerant. And it's not that easy. It depends on something called the dew point. That's the temperature at which the relative humidity is 100. The incoming air has to be cooled down below that dew point in order to be able to achieve that condensation of vapor and collection of decent amount of water. So the chart below shows the dew point at different temperatures and relative humidity. And for the region, basically we are in this particular regime of dew point. So which means that any device that works on the vapor compression refrigeration cycle bring the air temperature down 20 degrees or low to have some meaningful extraction of water. So that takes a lot of energy, But nevertheless, the ones that are commercialized in the market are based on this technology. And It's not just the energy consumption, it's also the use of refrigerants, for example, chlorofluorocarbons. They're environmentally damaging. Even people are researching more greener refrigerants to get that. It takes about 300 to over 1,000 watts per liter to produce water using this technology. And why is that so? Because of the temperature, the weather conditions. And as you can see in this chart, based on different parts of the globe, I mean, it's high. It's close to 250 and above in this region, in Asia particularly. So that's why the implementation of this technology at scale might be challenging unless there is more energy efficient systems are developed. The other principle is adsorbent-based materials, where there's a desiccant that absorbs moisture from the air, and there's a device that has that desiccant, and the dry air comes out. And usually you need some kind of stimulus like heat to remove water from the desiccant and convert it into adsorbent. That water is then condensed again as a liquid water and collected. So there are different materials that are used as desiccants. For example, silica gel, very common, and lithium and zeolites. Of course, the efficiency and productivity and all those, the cost and everything still have to be evaluated more thoroughly because this most of this work is still in For example, you can integrate these systems just like the previous vapor compression systems, or you have the device with the material, and there's a condenser. Whatever moisture is absorbed, basically, is the whole process becomes efficient. And of course, a lot of research, including in our group, what we are working on is different materials that require less energy to dissolve water, and also the system design that takes much less energy. And not just that, it also we are looking at using these technologies like solid desiccant and the liquid desiccant for applications in different regions. That means because some of the materials and the devices work in areas where the temperature is low or the moisture is high. But what about majority of relative humidity is not more than like 30-40%. So we are working on systems that are low energy, but also can be used in all environmental conditions. And hopefully in the next webinar, if I get a chance, I can talk more about this. We have done some economic viability and feasibility studies, and what we find is the payback period for a 2,500 liter per day device using atmospheric water harvesting system, using adsorbent based technology, is less than 2 years, which should be economically attractive. And as we found out, a bottling plant from a traditional mineral water plant that relies on RO disinfection, it's actually costlier than the bottling plant for so in conclusion, as we have seen, atmospheric water harvesting water, renewable water from anywhere. And with these new technological innovations, we can look to apply these technologies in any environmental conditions, in disaster relief areas, flood-prone areas, or remote areas. So and completely off-grid by integrating with solar. So these are all the main advantages. But finally, I would like to reemphasize something that I've mentioned already: the integrated water resource management for sustainable water security. So it is basically a blend, a combination of all these approaches working in tandem with each other. The production we have seen, so I think we're good there. Distribution and resource management. Of course, there's a need for green infrastructure for circular economy, and smart incorporation of the smartness into the water collection distribution networks, and of course innovative approaches to water storage, whether it can be centralized ponds or decentralized units within a community or even houses. And how we use that water also is very important. Of course, the consumption opt for more off-grid technologies or decentralized technologies or more smart methods within their facilities for either landscaping, irrigation, or water usage. And of course, recycling and reuse, it's more of an industrial process. There are technologies available, and a lot of innovations happening, not just to extract water from the wastewater, but also any minerals, for example, nutrients or salts. So all these are something that we are working on. Have given a good picture of what is needed for managing the stormwater, the urban stormwater, and the overall water security scenario. So with that, I thank all of you, and my details are there in case anybody needs to have a discussion about it.
Thank you so much, Dr. Gadibati, for the insightful presentation. And we've received few questions from our audience, and I'd like to begin with the first question, which is, what are the key challenges you foresee in implementing atmospheric water harvesting at scale in arid regions like the UAE?
That's important because most of the atmospheric water harvesting technologies are looking to UAE and the Middle East as the main ground for implementation. because of the several reasons I mentioned. But of course, it's not easy. It's not without any challenges. Mainly because the more mature technology is the vapor compression process that I mentioned that requires a lot of energy, right? And obviously, since UAE is also moving away from the carbon or fossil fuel energy and trying to look towards more sustainable methods, it is important that this technology is made more energy efficient. And not just that, even the refrigerants, for example, there has to be some new refrigerants that are, let's say, biodegradable or not environmentally harmful. And without challenges being addressed, I mean, yeah, it's difficult to implement at large. I mean, technically, yes, you can, but is it the cost that we want to pay?
Got it. Thank you. Thank you for the clarification. The second question says that how does the urban stormwater management complement rain enhancement effort, and what specific examples can you provide from the UAE or other regions?
Interesting. So the specific example of the whole integrated management approach is something that I mentioned with the Singapore as an example, and I think that tells a lot of story. But nevertheless, the whole idea is to manage that storm water or the rainwater after a particular cloud seeding event. It's not just about how much rainwater is achieved or rainwater is harvested during that process, right? How is it stored properly and used properly? And of course, these nature-based solutions that I mentioned, and the combination of all those, and then that can be done easily with infrastructural changes. Even if the development has happened, even if the road has been built, pavement has been built, these measures can still be incorporated, right? And of course, it's not a single solution, so they have to work with other water management solutions, basically that tie into the desalination, or water harvesting, or other methods. So it's basically a combination of all these efforts.
All right. And our last question is, given the techno-economic challenges associated with desalination, how do you see non-conventional approaches like cloud seeding and atmospheric water harvesting evolving to reduce reliance on desalination?
Okay, I'm more of a desalination guy, but I'll try not to be biased towards desalination. But having said that, I mean, see, there are techno-economic challenges, and there are research work going around the world. I mean, so pretty much every membrane scientist is working towards better desalination process to reduce the energy, reduce the chemical usage. I mean, but despite all these challenges, this is a very readily implementable solution that addresses the problem right now. And I'm sure this will continue in the future as well, with more and more innovations and more methods. But having said that, the cloud seeding again may serve as an intermittent stopgap arrangement for, let's say, a very quick short-term solution. But my money is more on, let's say, atmospheric water harvesting as a complementary technology to desalination. Mainly because, like I said, it can be used anywhere. And with any innovation that reduces the cost of implementation, it can be used basically in areas where desalination won't work, or where the coastal lines are far away, right?
Yeah, you're right. Thank you. Thank you so much, Dr. Gadibati, for sharing your valuable insights on sustainable water management and non-conventional technologies. Today's session provided a clearer understanding of the challenges and innovations that are shaping the future of the water security, particularly in arid regions like the UAE. And I'd also like to thank the audience for their active participation and thoughtful questions. If you have any additional questions or would like further information, feel free to reach out to us or visit our website, the UAE Rep. For your information, this webinar is being recorded and it will be available on our website. Stay tuned for our future webinars as we continue exploring the latest advancements in rainfall enhancement research and technology. Thank you all and have a great day ahead.